If one is honest about the current situation, China's economy is not doing particularly well. Many regions are facing debt crises, many young people are struggling to find jobs, and a lot of people are having a hard time making ends meet. Yet, given the sheer size of China, there is always room for hope. As the saying goes, if the east is dark, the west will be bright. If the south is in shadow, the north will shine. After years of groundwork, China's high-tech sector is now on the brink of a breakthrough. Especially over the past year, thanks to breakthroughs from AI companies like DeepSeek, Unitree Robotics, and Manus, as well as Trump's populist policies. By contrast, China's image on X, formerly Twitter, has not only been overwhelmingly positive, but also representative of advanced technology. In the eyes of many American netizens, China is not an enemy, much less a backward nation. It has become something to learn from, even something to envy. Of course, this sentiment isn't entirely objective. It mostly reflects disappointment with their own country. It's reminiscent of Enlightenment-era Europeans, during the reign of Louis XIV. Disillusioned by local religious conflicts and constant warfare, they romanticized the Qing dynasty, described by Jesuits as stable, prosperous, and civilized, turning it into an imagined utopia. The idealization has reached a point where some believe China is capable of anything. A wave of China hype has emerged in the US. The version of China on X is often far more powerful than the China portrayed in the domestic Chinese language sphere. But how advanced is China's tech sector, really? I'll try to offer a fair assessment. Several claims are currently circulating among American tech enthusiasts. Claims you've probably never seen on Chinese social media. China is preparing to build a Space 3 Gorges dam. A solar panel belt in orbit, 1 kilometer wide, capable of generating more energy annually than all extractable oil on Earth. China has just discovered 1 million tons of thorium in Inner Mongolia, which could power the country for 60,000 years via nuclear reactors. China is building an entire semiconductor supply chain domestically, covering every chip-making stage. Something no other country has ever attempted. Some even claim China's domestic EUV lithography machine has already been tested at Huawei's Dongguan plant, with trial production expected by Q3 2025 and mass production in 2026. If all of this were true, the US wouldn't be trying to choke China's tech development. China would be considering a tech blockade of the US. But the reality is, these claims are wildly exaggerated. The good news, however, is that there's a grain of truth in all of them. Chinese researchers are indeed working on big things. I don't have any insider information. Everything below is based on publicly available sources. After reading this, you'll have a more balanced understanding. And perhaps more importantly, a clearer perspective on what cutting-edge technology really means. Let's start with the Space 3 Gorges Dam. Generating solar energy in space has many advantages. Solar panels can constantly face the sun without interruption from day-night cycles or atmospheric scattering and absorption. Theoretical estimates suggest efficiency could be 10 times higher than on Earth. China indeed has a plan for this, but it's still in the conceptual stage. China's roadmap includes launching a wireless power transmission satellite to low Earth orbit in 2028 to test whether solar power collected in space can be transmitted to Earth as microwaves. This might be the energy receiver under test on the ground. If the experiment succeeds, a 100 kilowatt space solar power station will be built by 2030, scaling to 10 megawatts by 2035, and eventually a 2 gigawatt station by 2050. How big is 2 gigawatts? That's equivalent to a large nuclear power plant, capable of powering millions of households. Its annual output would be 17.5 terawatt-hours, TWh. Not a small number, but still far below the 100 TWh generated yearly by the Three Gorges Dam. And as a fraction of global oil used for electricity, a 2 gigawatt station would contribute less than 0.1%. Let alone compared to global total oil reserves. So, this is not a world-changing project. The Space 3 Gorges Dam was first reported by the South China Morning Post on January 9, 2025. They never claimed it would rival global oil reserves. But after English-language media widely reprinted the report, someone added this exaggerated claim. In reality, this technology hasn't even completed basic feasibility validation. You could call it a form of scientific science fiction. It might not even be a Chinese original concept. Similar plans exist in Europe, the US, and Japan. China seems more focused on ensuring it has a seat at the table, not on monopolizing the initiative. EUV lithography machines are national strategic assets. EUV machines are essential for producing chips smaller than 5 nanometers. Currently, only ASML has the capability to manufacture them, and the US has demanded an export ban to China. EUV is the biggest bottleneck in China's semiconductor industry, and a decisive factor for future AI development. We've covered Chris Miller's Chip War, which explains how hard EUV is, especially the light source. EUV light has a wavelength of just 13.5 nanometers and must be generated artificially. ASML's method is laser-produced plasma, LPP. Tiny 30 nanometers tin droplets are shot through a vacuum at high speed, then hit twice by high-powered lasers to form plasma, emitting EUV light. This system took the world's top researchers 20 to 30 years to perfect. The most critical component is the carbon dioxide laser that hits the tin droplets. Only TRUMPF in Germany can make this laser, which contains over 450,000 parts. China did not adopt ASML's approach. Instead, it is pursuing two alternative EUV light sources, hoping for a leapfrog advantage. The first is Harbin Institute of Technology's laser-induced discharge plasma, LDP, method, developed by Professor Zhao Yongpeng's team. It also uses lasers to vaporize tin, but avoids the precision-required nanodroplet generation and the need for carbon dioxide lasers. Instead, it creates a tin vapor cloud between electrodes, then applies high-voltage current to ionize it into plasma, emitting EUV light. There are two challenges. 1. Precisely timing the laser vaporization and electrical discharge for stable EUV output, and 2. Electrode erosion by the tin plasma, which forces reduced discharge frequency, limiting power. ASML tried this path, but gave up due to the low output. However, Zhao's team made a major breakthrough in 2024, received a technology award, and began cooperating with a Shanghai firm to develop a prototype EUV light source for lithography. How exactly they solved these problems, and with what performance, we still don't know. The second method, from Tsinghua University, is a steady-state microbunching storage ring accelerator, SSMB. This involves building a circular particle accelerator to generate synchrotron radiation via electron beam interactions with lasers and magnetic fields, producing EUV light. In 2023, Tsinghua completed feasibility testing, proving the physical theory. Its main advantage: massive EUV output. Basically, you'll never run out. But high intensity brings problems too. Transmission loss, component damage, and complex mirror alignment. The accelerator is expensive, so to be cost-effective, multiple lithography machines must surround it in a megafactory setup. This project is still on paper, but plans to begin construction in Xiong'an. Ideally, Harbin's approach could solve the short-term EUV light source issue, while Tsinghua's might eventually overpower ASML with scale. But there are many uncertainties. Even with a light source, many other components remain. How to make mirrors that can reflect EUV, how to achieve nanometer-level precision, how to fabricate EUV masks. ASML's supply chain includes over 1,000 global partners, all working together under a unique management model. If any Chinese firm is to replicate that role, it might be Huawei. Though Huawei has never officially committed to this task. That viral image online? It's not a full lithography machine. It's an objective lens alignment interferometer, used for calibrating EUV lithography optics. Having one indicates some optical breakthroughs. Until now, only Carl Zeiss, in Germany, could make such lenses. In short, while progress is real, it's hard to believe China will develop a commercial-grade EUV lithography machine anytime soon. China hasn't even fully localized deep ultraviolet, DUV, machines yet. Thorium-based nuclear power, however, is a far more credible project. one where China is clearly ahead. Unlike traditional reactors that use uranium-235-238, thorium offers a different route. You irradiate thorium-232 with neutrons to produce protactinium-233, which decays into uranium-233, a fissile material similar to uranium-235. This is the thorium fuel cycle. Thorium has many advantages. It's far more abundant, 3 to 4 times more than uranium, and easier to mine. It's cheap and available not just in China, but also in Brazil, India, Australia, and the US. Thorium reactors generate less nuclear waste, and the waste has shorter half-lives, making disposal easier. In terms of safety, thorium reactors require high temperatures to start, but operate at low pressure, making catastrophic accidents unlikely. No need for high-pressure water cooling means easier inland deployment, not just near oceans. Of course, thorium tech has challenges. 1. It emits gamma radiation requiring robust shielding. 2. Most thorium reactors are molten salt reactors, MSRs, and molten salt may corrode pipes and equipment, requiring special materials. But these issues seem solvable. So why aren't thorium reactors mainstream? Mainly historical inertia. Early nuclear power tech came from weapons development, and countries wanted reactors that could also produce weapons-grade materials. Something thorium can't do. Once uranium reactors matured, entire industries grew around them, leaving little incentive to switch. As early as the 1960s, the United States Oak Ridge National Laboratory had conducted research on thorium reactor technology. After some evaluation, the project was abandoned. Now, China is clearly in the lead. As early as 2021, China built an experimental thorium reactor, which received an operating license in 2023 and already has power generation capabilities. In 2025, China plans to begin construction of a 10-megawatt thorium-based molten salt reactor power plant, which is expected to be completed before 2029 and will be capable of supplying electricity to 100,000 households. By 2035, China also plans to build a 100-megawatt commercial thorium molten salt reactor. In contrast, thorium reactor R&D in the United States is currently being pursued mainly by a few private companies. One company, Flybe Energy, focuses on design, while another, Thorcon, plans to build a 500-megawatt molten salt reactor in Indonesia, though the project has not yet started. India, Japan, and Europe also have related research efforts, but they are all far behind China in terms of progress. In this light, if controlled nuclear fusion remains out of reach in the short term and uranium ore prices stay high, thorium reactors could provide China with a continuous and stable energy supply. If China manages to develop a complete system for this technology, it could become an exporter of thorium reactor solutions to the world. In summary, although China's current level of science and technology may not have reached the sci-fi standards imagined by some netizens, it has already achieved remarkable progress. What we've covered here is only part of the story. China is also in the global first tier when it comes to fields like aerospace. At least in high-end manufacturing, China is no longer simply imitating technologies from developed countries, but has developed independent innovation capabilities and its own technological discourse. In some areas, China is advancing in step with global peers, with a strong presence. In others, where it faces technological blockades, China is determined to develop alternative paths, possibly even leapfrogging its competitors. And in a few cutting-edge fields that have not yet been widely explored, China has already made the first breakthroughs and become the global leader. That said, we must also recognize that the overall standard of Chinese manufacturing has not yet reached the top-tier global level. Being excellent does not mean being top-tier. For example, China still heavily relies on imports for high-end medical equipment. In the area of high-end CNC machines, although China is now able to produce 5-axis machines, their precision still lags behind those made in Germany and Japan. More complex 7-axis machines are still imported. While Chinese fighter jets now use domestically developed thrust vectoring engines, due to material and process limitations, the lifespan of these engines is only about 1/4 that of their Western counterparts. This current situation can be described using the 80-20 rule. If the global technological frontier represents 100%, then reaching 80% can already be considered excellent. And excellence is scalable. If you continue to invest funding, attract talent, and remove obstacles, you can reach an excellent level, especially when the feasibility of the technology has already been demonstrated elsewhere. In such cases, 20% of the effort can get you to 80% of the capability. However, moving from excellence to greatness, from 80% to 100%, is an entirely different game. The path forward becomes unclear. This isn't just a matter of one technological breakthrough, but requires full industrial ecosystem support, cross-disciplinary collaboration, foundational scientific research, and, most importantly, international innovation partnerships. The hardest problems are rarely solved by any one country acting alone. To achieve that final 20%, we must invest 80% of the effort. China is now in a critical transition from excellence to greatness. Blind optimism would be unwise. But the number of competitors ahead of us is rapidly shrinking. And right now, there's an opportunity. Trump is creating a window for China to overtake. Both Trump and Elon Musk are pushing to cut U.S. science funding. Yet much of America's scientific strength has relied on government-backed research institutions, universities, and national labs. If agencies like NASA struggle to get funding, the pace of U.S. technological advancement will inevitably slow. Meanwhile, the U.S. is distancing itself from its allies and reducing international cooperation. China may not even need to overtake on a curve. At this rate, simply staying the course on a straight path might be enough to take the lead. That's it for today's content. Thank you for watching, and I'll see you in the next video.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.